Hi guys, this is Bob. In this video, I'm going to talk about types of failure and the basic concepts of fracture mechanics. As the very first thing that we learn in this semester in this course, there are plenty of abstract concepts in this chapter. So, basing on my own experience on learning, it is better to understand a concept from our daily but not just from the book. I like watching movie in daily life, so firstly, I have two film clips recommend to you guys, and the clips are from Final Destination 5 and Spider-Man 2. Here it is.
Whoa! The hell? Peter, did you feel that?
What?
Something's wrong.
We're slowing down.
We can notice that in Final Destination 2, the failure of steel cable, the bridge desk triggered a series of chain reaction, and then the whole bridge broke. And in Spider-Man 2, Peter Parker used dozens of spider silk successfully pulled a high-speed subway full of citizens. During this period, several spider silk failures one by one because it could not bear the energy of pull. These two clips all show the phenomenon of failure. Then see in sense through phenomenon. What is failure? In the textbook, failure is defined as having occurred with the plastic deformation reaches an arbitrary limit, such as the 0.2% offset in a standard tensile test. Often, more yielding can occur without harm. One of the most greatest Chinese Chairman Mao said, "Practice is the only criterion of testing truth." Last week during 2MT Lab, the structure and the properties of material, Professor Doris let us make an experiment called tensile testing. Through this test, we learned how much tension an iron cylinder could break under, including the changes in the image during the whole process and the sectional morphology of the iron coulomb after breaking. This experiment has been carried out successfully, and we have obtained correct images and relatively perfect experimental phenomena result. But what is the essential reason for this phenomenon? In order to explore this problem, I decided to explain it from the micro level. Under the microscope with a magnification of 400 times, we can observe the microstructure of iron, including carbon distributed in it and some clear lines. It may still be difficult to understand just through this picture. So, the first step of the thorough understanding is to abstract an image in your own way. I will continue to enlarge the multiple and cartoon the image. Through this concrete cartoon, we can easily understand that in the microstructure, there are many extremely small cracks distributed inside the iron. These cracks are the culprits that cause the iron to break. When the iron is stretched, these cracks will be torn to a greater extent due to the force. When the size of crack reaches a certain limit, the entire iron coulomb will break. Then this is what we call failure. The definition of failure by distortion is arbitrary and not always easy to apply, and materials prone to distortion failure are classified as ductile. and those prone to fracture without significant prior distortion as brittle. Meanwhile, static loads can cause large deflection and elastic instability, and plastic deformation and fracture are the topic of this chapter, the main topic. You might still remember the cartoon minor fissure that I talked just now, and this small fissure leads to the second topic we will discuss today, the fracture mechanics. To begin with, we need to figure out what is the stress intensity factor. The fracture mechanics method first assumed that all real materials contain cracks of a certain size, even if there are only micro cracks. If brittle fracture occurs, it is because of the load and the environmental conditions that one or more original cracks almost fail to expand instantaneously. However, if there is a fatigue load, the initial cracks may expand until one of them reaches the critical size. In this video, I will not explain the practical application of this topic, but it is necessary to show you the 3D image for a more intuitive understanding. In the fracture mechanics method, the stress intensity factor is evaluated as K. K is then compared with a limiting value of K that is necessary for the crack propagation in the material. This limit value is a characteristic of material called fracture toughness or critical stress intensity factor, KC, which is determined by standard tests. At the same time, failure is defined as when the stress intensity factor K exceeds KC. Therefore, the safety factor SF of a fracture failure can be determined as Kc over K. Most currently available values of K and Kc are for tensile loading, which is called mode 1. Accordingly, these values are designated as Ki and Kic. The material is roughly in a plane strain state. Most of the available values of Kic are applicable to relatively thick members. However, the crack root material in a sufficiently thin material provides a plane stress condition, and the KIC value of plane strain is much lower than that of plane stress. Therefore, when the thickness is unknown, the KIC plane strain value that is easier to obtain is useful for conservation calculation.